Great, thank you. So in this talk, I'd like to tell you about the Tumult platform. So it's a system for safely releasing aggregate information from sensitive data sets. And it supports a variety of a workflow where you can take a source data set and transform it in various ways before taking that data and aggregating it to statistics that are safe to release. So the platform will soon be available open source, and it's currently in use at several organizations. In fact, as you heard in the first couple of speakers today about the deployments at IRS and Wikimedia, it's also in use at the US Census Bureau, and there's a talk tomorrow that's going to talk about one of the census use cases. So in building this system, we had 4 primary design goals, and so in today's talk, I'd like to tell you about those goals and then explain how we built the system to achieve them. So the first goal is about usability. So we want any data scientist or engineer to be able to successfully use the platform to solve real-world problems. No expert-level math knowledge or in-depth understanding of DP theory should ever be required. We want the platform to be easy to use by non-experts, but at the same time, we want the platform to empower them to build complex privacy solutions. So the second goal is about privacy. So we want an analyst to be confident that the aggregates computed by the system are safe to release, share, whatever. And so the system offers this assurance by providing a provable guarantee of differential privacy. So you've already heard about that in a few different talks, but it's a rigorous model of privacy protection. These days, it also comes in many sort of variants with different parameterizations. And so the system should allow the user to select the appropriate variant of DP and parameter settings that make sense for their use case. Some scope clarification, so we're in the kind of central DP model with an analyst who is trusted to use the tools as intended. So things like local DP or adversarial analysts are out of scope, at least at the moment. The third goal is that the platform be extensible. And I want to emphasize this point. So it should be possible to add new transformations or aggregation functions and even variants of differential privacy without requiring deep refactorings of the code. And we felt that this was really important because we're really trying to build this platform with growth in mind. And the users that we've worked with so far have actually surprised us with requests for features that sit right at the kind of frontier of DP research. And of course, that frontier is also expanding. And so we want to be able to add to the platform, new mechanisms that are developed in literature and new methods of privacy accounting, as soon as they're developed. And the final goal is about performance. So we designed the platform to scale to large inputs. The computation needed for DP may introduce some overhead, but we aim to have performance that's sort of on the same order of magnitude as what you might get if executing computations without the DP part, say on Spark. So those are our design goals. I'll now talk about how we achieve them. So our platform is composed of layers, and with each layer focusing on a different subset of the design goals. So the topmost layer is analytics, which offers an easy-to-use but powerful API. So analytics is intended for data scientists. They don't need to be experts in DP, and we hope that the Python interface will feel familiar to users of, say, Pandas or Spark, because it has similar functionality and a similar programming style. I'd like to show just a brief code snippet here. So to use it, the data scientist first creates a session where all interactions with the data are guaranteed to be differentially private and not to exceed the privacy budget specified by the user. The user can then write a query on this private source. So this particular query filters the records to keep only individuals older than 42, groups the data by zip codes, and computes a median for each zip code. The query is evaluated by a DP computation engine using the user-specified privacy budget. And then the cumulative privacy loss is tracked by this session, and the analyst can query it at any time to find out how much budget is remaining in the session. So that was a simple example. Of course, real-world use cases are often more complex, and our platform has evolved rapidly to support the needs of our users. So I can kind of categorize those needs into 3 broad themes. So first, users want to add the minimal amount of noise to ensure privacy. And to minimize the noise, you often have to do careful privacy accounting behind the scenes, and so we've added some features to support that. Another aspect is data adaptivity. So users often want the granularity of the statistics to be as detailed as possible. But of course, DP actually prevents you from publishing detailed statistics about small groups of people. That's by design for privacy protection. So data adaptive workflows, the idea behind them is to sort of drill down in dense regions of the data, but in areas that are sparse, where there aren't many records, maybe instead publish coarser summary statistics. And finally, users want to perform data transformations that are complex in terms of the kind of privacy calculus needed to support them. So just as an example, a flat map takes one single private row and explodes it into multiple rows. And so the system must somehow track this kind of explosion of private data in order to add the appropriate amount of noise. So all the features shown on the right there have been added to analytics. And one of the greatest challenges we faced is how to incorporate all these sophisticated features and get them to kind of interoperate effectively. And so to respond to this challenge, we created Tumult Core. So Tumult Core is the privacy framework that powers analytics. It's designed to provide provable privacy guarantees and be easily extended. So Tumult Core is, so I'd like to tell you a little bit about Tumult Core. So it's a collection of composable components for implementing DP algorithms. It consists of transformations and measurements, which you can think of as like, basic DP mechanisms like the Laplace mechanism. Each component explicitly encodes its privacy properties, and I won't get into the details of what those properties are, but really the point is that these properties are declared, and then they're available for inspection, say by a user or by other system components. But really the power of Core actually lies in its ability to combine these base components into more complex algorithms. So think combinators like chaining and composition and others make it possible to derive new measurements and transformations from these base components. And crucially, the privacy properties of the new component is derived automatically from the properties of the components that are being combined. One kind of final remark about Core is that this is the privacy critical code. It's the really critical pieces, and it's important to implement them carefully and scrutinize for potential bugs. And that's one of the motivations for making this code open source, is so that we can get many eyes looking at the code. So I just mentioned that we have a paper at TPDP this year, a differential privacy workshop, describing our approach to handling floating point vulnerabilities, which have vexed the DP community for quite a while. And this can help make safe versions of things like the Laplace mechanism. So that's Core. So it enables the creation of complex algorithms from basic building blocks. Everything in Core and everything you can build with Core comes with an explicit inspectable privacy guarantee, and its modular architecture is highly extensible. Of course, all this actually makes Core pretty difficult to use on its own. These explicitly encoded privacy properties kind of only make sense if you have a background in DP, and this emphasis on kind of modularity and extensibility means that a lot of the components are fairly abstract and kind of awkward to use. But the analytics layer takes this functionality and kind of packages it to support common workflows that we see and make it more usable. So the analytics layer provides usability, the Core layer gets us provable privacy and extensibility, and to achieve scalability, the platform is integrated with Spark. And so I'll skip the kind of details of our scalability experiments, but I'll just say that we can take complex iterative algorithms and scale them to inputs of, say, up to 1 billion rows, and the runtime seems to scale linearly with the input size on a fixed cluster. So that was a brief overview of the platform. We think that the Tumult platform is really, I think, the only DP platform out there that provides this particular combination of usability, extensibility, and scalability. And we hope that a data scientist without DP expertise can confidently use the platform to compute differentially private statistics. And that confidence comes from the kind of explicit privacy guarantees of Core that are encapsulated in this kind of end-to-end privacy guarantee explicit in the session interface, and the fact that the code will soon be available open source. So that actually brings me to my last point. So if you're wondering how soon you can get access to it and try it out, I have some good news. So we're super excited to announce that we've released it open source. So We pushed actually really hard to get this out in time for PEPR because we think this is a great community to kind of share this code with and hopefully gather your feedback. So we'd really love to hear from you. If you're interested, there are links here, but we'll post some links in the PEPR channel, PEPR Slack channel as well. So thank you.